Hello everyone. The product of our group is Vegemite. Vegemite has history over the 90 years and it was begun in 1992 by Kraft Food Company. Vegemite is made of brewer's yeast, which contains a high level of vitamin B, and Vegemite is invented by Dr. Cyril and named by the public. Maybe you want to know why Vegemite is so popular. One of the reasons is the nutrition benefits. The vitamin B in Vegemite, especially for riboflavin and folic, is so good to health, and Vegemite turned to an indispensable part of Australian eating habit. One of the frequently asked questions is how do I store Vegemite? The answer is Vegemite is a shelf-stable product because of its low water content, so Vegemite don't need to refrigerate. The fluid performance of Vegemite that we will study below are spreading, yield stress, shear thinning, and sexotrophic behavior. In the followed part of our presentation, the test we are going to do are squeeze test for shear thinning and slump test for yield stress, and we will do a stirring test by egg beater to test the sexotrophic behavior of Vegemite.
Yield stress is the key rheology parameter for high concentration non-Newtonal fluid. Samples flow downward and lateral because of gravity. Yield stress resists downward flow and viscosity resists lateral flow. Slump test is filling samples into cylinders that open up and down. Then left cylinders. The height between the harvest point after clumps and initial is called slump. 3 samples of our experiment are Vegemite, tomato sauce, and honey. Now let's enjoy the video. First, filling samples into 2 cm tall cylinders. Then, take cylinders away. Different degree of slump in 3 samples has been shown. As you can see, slump of honey is high. In contrast, Vegemite size and shape has nearly no change. Results showing below. Slump of samples are respectively 0, 11, 17 mm. The yield stress from high to low is Vegemite, tomato sauce, and honey. Inverse relationship between slump and yield stress can be clearly defined.
Why did Vegemite perform so high yield stress? We can explain from the microstructure of the dominant ingredient, beta-glucans. The beta-glucan from yeasts, 1,3-beta-D-glucan, is insoluble polysaccharide. Its structure is as these pictures, showing linkage and the overall structure. Basically, 1,3-beta-glucan is a kind of polymer that form a network. As this, they are able to absorb and keep water, finally create a restrict swirling. The network formation showing rigid structure, giving a continuous but easily broken network, like a kind of weak gel. This formation is easily to be destroyed at a higher shear rate, but not at zero shear rate. As this experiment results, even only 13% of 1,3-beta-glucan in liquids, which much lower than that in Vegemite, can cause high viscosity at zero shear rates, as well as significant high yield stress.
What you see here is our product, Vegemite, in a plastic bag flowing out of the hole. If we observe closely, at first, Vegemite does not flow on its own, although there is a hole made in the plastic bag. When stress is applied, we begin to see the flow. Also, you can see that when stress ceases, so does the flow. The basic principle behind the phenomena is shown in the figure, explaining how yield stress is related to Newtonian and non-Newtonian fluid. Take an example of a Newtonian fluid, let's say water. We all know that water flows at any shear stress. Force is not necessary. But Vegemite will experience flow or velocity only when certain yield stress is applied. Shear thinning experiment by manual stirring. Vegemite at its original state is taken in a plastic bowl and manually stirred for quite some time. Clearly from the video we can see that we underestimated the force or stress required to reduce the viscosity of fluid and prove its shear thinning properties. Obviously, Manual stirring did not yield enough stress or force to explain how shear thin Vegemite flows or behaves when viscosity is reduced. Now by mechanical stirring. The same bowl of Vegemite was stirred again using egg beater. This was done in order to achieve a high shear rate, better result, and to conduct experiment in the less time. As you can see, Vegemite was mechanically stirred at a high shear rate, and after some time, what we observe is that it explodes or spats out of the bowl. What can be the reason? As the mechanical stirrer goes deeper into the bowl containing Vegemite, viscosity of each layer reduces, and as it reaches the very last layer, due to shear thinning, the shear thin Vegemite flows or spats out of the bowl, proving its shear thinning properties.
Shear thinning is another obvious rhenology property of Vegemite. From the previous video, it can be seen that the Vegemite becomes more fluid-like during stirring, and finally it spilled around. However, why did Vegemite show shear thinning instead of shear thickening, or just Newtonian? We can get some clues from its ingredients. Vegemite is a concentrated yeast extract, and as a result, it makes protein occupy 1/4 of its weight. 100 grams of Vegemite contains 26 grams of protein. Then you may wonder, what's wrong with protein? You were talking about shear thinning. According to tons of literature review, we found that protein is the highly possible reason for the shear thinning phenomenon. Many researchers have shown that protein or peptide can form a network with various non-covalent interactions, such as electrostatic, hydrophobic, pi stacking, hydrogen bonding, and conformal changes, which give an illusion of thickness. Once shearing force is applied, the network will be broken, and the fluid will become less viscous. While shearing stops, the network reforms and viscosity increases again, which is also called self-assemble in some papers.